So in this class we will discuss about PN junction. So how PN junction is created? First of all we have to see when a p-type semiconductor, suppose this is p-type semiconductor and n-type semiconductor, if it is joined, then the contact of this p-type and n-type, this contact is PN junction. Okay. So as we know that in case of n-type semiconductor, the majority carriers are free electrons, whereas in case of p-type semiconductor, the majority carriers are free holes. So we have to see when these two semiconductor materials are combined, are joined, then at the junction, what happens to the free electrons and to the holes? Okay, so we will see that. Suppose this is p-type semiconductor and this is n-type semiconductor. So in case of n-type semiconductor, the majority carriers are electrons, and in case of p-type semiconductor, the majority carriers are holes. It is represented like this and it is hole. Okay. Now, and here the minority carriers are, this is majority carrier and minority carriers are holes, and here minority carriers are electrons. Okay. Now, when p-type semiconductor is connected to n-type semiconductor, then what happens? The electrons, that the majority carriers in n side, these are electrons. Electrons start to diffuse from n side to p side, from n side to p side across this PN junction. This is PN junction. After combining these two semiconductor, the electrons, which are the majority carriers in case of n-type, it tries to diffuse from n side to p side. Okay, and here the majority carriers are holes. Okay, so after combining, when this electron, it is diffusing from n side to p side, so this electron and hole, these recombine, these two carriers recombine. Okay, so after recombination, what will happen? Across the PN junction, we will see you can see this is donor end and this is acceptor end. At the start, electrons tries to move from n side to p side. Means electrons diffuse from n side to p side, and after combining electron and hole, these fixed charges is found near the junction. Because of this, these are static in nature. Okay. So here it is acceptor end and here it is donor end. Okay, and here you can see these are electrons. and we can see here like this holes. And magnetic carriers are electrons. And here magnetic carriers are holes. So what happens when p-type and n-type it is combined? When it is combined, the electron side it tries to diffuse to p side. Okay, so electron and hole this recombine across the junction, leaving behind only acceptor and donor ion. Only in this figure we can see that only acceptor ion and donor ion is present because of the absence of, you can see here, absence of free carriers. Absence of free carriers are seen across this p-n junction. So we can say that this region is depletion region. This region is depletion region. And this is positive and this is negative voltage, okay, and this is say V0. So because of the creation of depletion region, how depletion region is created? Here you can see there are no any free carriers. So because of the absence, because of the depletion of the carriers, it is known as depletion region. And because of the creation of depletion region, then the electrons it will not move from n side to p side after the creation of the depletion region. Okay, so it provides a barrier. It provides a barrier to the carriers. Okay, so the potential that is created, the potential difference that is created due to this, it is known as barrier potential. And it is represented as V0. This is V0, this is positive potential and this is negative potential. So potential difference between this is V0. V0 is barrier potential. So if we are giving some potential which is greater than the barrier potential, then only further recombination or further movement of carriers may take place. Okay, so we have seen how depletion region is created, how barrier potential is created. Now the electric field, what will be the direction of the electric field? Direction of the electric field, it is from positive terminal to negative terminal. Direction of the electric field, this is the direction of the electric field. This is positive terminal and this is negative terminal of this potential V0, barrier potential. Okay, and barrier potential, it is equal to 0.3 volt and it is equal to 0.7 volt for germanium and for silicon. If p-type and n-type semiconductor, if it is made up of silicon, then in that case V0 it is equal to 0.7 volt, and similarly V0, that is barrier potential, it is equal to 0.3 volt if this p and n type it is made up of germanium atom. Okay, then we will see this is without any external bias voltage. Okay, then we will see if some external bias voltage is applied to P and N type semiconductor, then what will happen? Okay. External bias, okay, to PN junction. This is P type and this is N type. So there are two types of external biasing. First one is forward biasing or forward bias, and second one is reverse bias. So what we do in forward bias? In forward bias, P-type semiconductor, P-type is connected to the positive terminal of the external battery, and N-type is connected to the negative terminal of the external battery. So this is forward bias of PN junction. Okay. Now you can see this is okay. Okay. So in this case, in forward bias, what happens? In forward bias of PN junction, what happens? Positive terminal of the battery is connected to P-type semiconductor, and negative terminal of the battery is connected to N-type semiconductor. Because of this, earlier, what is the direction of the electric field? Direction of electric field due to the potential barrier, due to this depletion region, it is like this. Now if we are connecting PN junction diode like this, then what will be the direction of the electric field? From positive to negative. Okay. So the direction of electric field provided by this forward bias, it is in opposite with the direction of electric field that is due to these fixed ions. This is donor ion and this is acceptor ion. Because of these fixed ions, there is an electric field. So the direction of electric field, which is given by this potential, this external bias, it is in opposite with this electric field. So the depletion region, it starts decreasing, and once if this E is greater than or equal to 0.3 volt, and if it is greater than or equal to 0.7 volt in case of silicon and in case of germanium, then what happens? This starts decreasing. This is the depletion depth. Okay, this starts decreasing with the increase in this forward bias voltage. So once if E is greater than or equal to 0.3 volt, if PN type is made up of germanium, and if E is greater than or equal to 0.7 volt, if P and N type is made up of silicon, then what happens? This depletion region or depletion depth, it starts decreasing, and under this condition it is almost equal to 0. So depletion region vanishes. Okay. So the conduction can take place once the depletion region vanishes. So we can see that after this voltage the current it starts rising, it starts increasing. Okay. So this is about forward bias. Then in reverse bias what happens, we can see reverse bias means P type is connected, P and N, P type is connected to negative terminal of the external battery and N type is connected to the positive terminal of the external battery. Okay. See, earlier the direction before this connection, what is the direction of electric field due to ions, due to fixed ions? It was, this is positive, this is positive, this is positive, and this is positive, negative ion. Okay. This is acceptor ion and this is donor ion. Direction of the electric field is this much, is in this direction, direction of electric field. Now here also the direction of the electric field is in this direction. Now after connecting in reverse bias, both the electric field are in the same direction. It means that the depletion region, so region it increases. Because of this, the depth of the depletion region or height of the depletion region it increases. So you can see the depletion region, this is depletion region increases, the depth of the depletion region it increases because of the electric field, these two electric field in the same direction. Okay. So with the increase in depletion region, no movement of free carriers take place, because the depth of the depletion region is too much, so that the free carriers cannot move freely. Okay. So practically the current, diode current, it is equal to 0, but practically it is not equal to 0. It is ID, it is equal to the reverse saturation current, means the current that is produced due to the minority carriers. So in case of reverse bias condition, ID is almost equal to 0. Okay. So we will see the VI characteristics of a PN junction. So suppose this is P type and N type. So this is a PN junction diode. It can be represented like this also. This is P side and this is N side, anode and cathode. Okay. Now we will see the VI characteristics of PN junction diode. This is forward bias voltage, reverse bias voltage, this is forward current, and this is, say, reverse current. Okay. Now this is 0 axis, 0.1, 0.2, and this is 0.3 volt. This is 0.7, say this is 0.7 volt, and up to 1 volt. Okay. Then what is this graph? This is the VI characteristics. This is the VI characteristics of a PN junction diode. PN junction diode. Okay. So in this graph, what we are saying? This is for germanium PN junction diode, and this is for silicon PN junction diode, and this is for germanium 1 microampere. This is for germanium, and this is for silicon PN junction diode. Okay. Now you can see that in case of germanium PN junction diode, if this is forward bias voltage, if VF it is greater than or equal to 0.3 volt. What is this 0.3 volt? 0.3 volt is V0. V0 is potential barrier voltage for a germanium PN junction diode. And if it is greater than or equal to 0.7 volt, then only the current starts rising in exponential manner. Okay. So you can write ID, it is equal to I naught into e to the power Vd divided by eta Vt minus 1. Okay, this is the equation of diode current in forward and in reverse bias condition. Okay, we will see. So in forward bias condition, what happens? In forward bias condition, Vd is always positive, and what are all? You can write ID is diode current, or you can write PN junction diode current. It is PN junction diode current. What is this Vd? Vd is potential or voltage applied to the diode, to the PN junction diode. Okay. Similarly, what is eta? Eta, it is equal to 1 or 2 depending upon the material of the diode. If it is germanium, it is 1. If it is silicon, it is 2. Okay. Now, what is Vt? Vt is equal to Kt by Q, where K is Boltzmann constant, T is temperature in Kelvin, and Q is the charge on electron. Okay, and Vt is volt equivalent of temperature. So Vt it is equal to approximately 26 millivolt at 300 K. That is at room temperature, it is approximately equal to 26 millivolt. This is volt equivalent of temperature. Okay. So this is the equation of diode current in forward and reverse bias condition. Okay. Then we will see in forward bias condition, this Vd is positive. Okay. So ID it is equal to I naught into e to the power Vd by eta Vt minus 1. So it is written as I naught into e to the power Vd by eta Vt minus 1. Okay, minus, you can write minus I naught. Okay, what is I naught? I naught is reverse saturation current. I naught is reverse saturation current. So reverse saturation current, it is due to the minority carriers in reverse bias condition. Okay. So in forward bias, we can write ID, it is approximately equal to I naught into e to the power Vd by eta Vt. Okay. Okay. So this is the expression for the diode current in forward bias condition. Similarly, in reverse bias condition, Vd is negative. So exponential of negative voltage, it will be very small quantity. So it is equal to, you can write I naught into e to the power Vd by eta Vt minus I naught. Okay. So if Vd is negative, then exponential of negative quantity, it is very small. So it is approximately equal to approximately equal to 0, and this is minus I naught, means minus reverse saturation current. Okay. Now so we are saying this is I naught and this is I naught for germanium, and this is for silicon, minus I naught. Okay. Then this is 0.3. So this is knee voltage. You can write knee voltage, and this is also knee voltage, 0.7 volt. And this is breakdown voltage. This is breakdown voltage. Okay. So in case of forward bias, Vd is positive. So once Vd is reached at 0.3 or more than 0.3 volt, then it starts. Then the diode current, this is diode current, forward bias current IF. Okay. So in this case, ID will be equal to IF. Okay. So diode current, it starts rising exponentially after 0.3 volt. For germanium and for silicon, it is after 0.7 volt, it rises exponentially. Okay. So this is knee voltage. So what is knee voltage? Knee voltage is that voltage after that voltage the current rises exponentially. Forward current, it rises exponentially. Then what is, then we have to see in reverse bias condition. In reverse bias condition, Vd is negative. Okay. So just now we have seen if Vd is negative, then in that case ID will be equal to approximately, it is equal to minus I naught. So here you can see it is approximately equal to minus I naught. For this is for silicon and this is for germanium PN junction diode. Okay. Now in case of in reverse bias condition, if the reverse voltage it increases, then we can see that at certain voltage it starts rising tremendously. Okay, at this point. So this point it is breakdown voltage. This is the breakdown voltage for germanium PN junction diode. This is the breakdown voltage for silicon PN junction diode. So breakdown voltage is that voltage, that reverse bias voltage at which the reverse current it starts increasing tremendously. So this voltage, at this voltage the diode it may damage. So we have to not give this amount of reverse bias voltage, because the diode may completely damage at this voltage. Okay. So we can see that this is I naught for germanium PN junction diode, and this is the I naught for silicon PN junction diode. This is in picoampere range, this is in microampere range. Okay. So we can see that the reverse leakage current in case of germanium PN junction diode, it is very much more as compared to silicon PN junction diode. And here you can see that the reverse breakdown voltage of a silicon PN junction diode, it is higher as compared to the reverse breakdown voltage of a germanium germanium p-n junction diode. Okay, is this clear to all of you? This, what is this VI characteristics? How to plot this VI characteristics of a p-n junction diode? This is the breakdown voltage. So in this figure we are seeing that the breakdown voltage of a silicon p-n junction diode is higher as compared to germanium p-n junction diode. We will study about the VI characteristics of germanium, silicon and gallium arsenide. Okay, so germanium and silicon, these are single crystal semiconductor, whereas gallium arsenide, it is compound semiconductor. Why it is compound semiconductor? Because gallium arsenide, it is made up of two different semiconductor materials having different atomic structure, and germanium and silicon, these are made up of single crystal semiconductor structure. Okay, so germanium and silicon, these are single crystal semiconductor, whereas gallium arsenide, this is compound semiconductor. So we will see the VI characteristics of all the three. So this axis represents forward bias voltage, this axis represents reverse voltage or negative voltage. This is forward current in milliampere range, and this is the reverse current or reverse leakage current in say microampere range. Okay, now see, this is say 0.1 volt, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 8, 0.9, 1, 1.1, 1.2, say 1.3 volt. Okay, and say this is 50 volt, say this is 100 volt. Okay, this is the forward VI characteristics in case of germanium semiconductor. This is for silicon. This is for gallium arsenide. See, this is the VI characteristics of germanium, silicon and gallium arsenide. Okay, so in this figure we can see that this is knee voltage. Knee voltage. Similarly, this 0.7 volt, this is also again knee voltage. Again this 1.2 volt, this is knee voltage. So knee voltage for a silicon diode, it is for silicon, it is it is 0.7 volt. For germanium, it is 0.3 volt, and for gallium arsenide, it is 1.2 volt. So these are knee voltages for germanium, silicon, and gallium arsenide based p-n junction diode. Okay, so this is 0.3 volt, 0.2 volt, all these are in volts. Now we are seeing that the reverse leakage current I naught, it is maximum in case of germanium, and it is minimum in case of gallium arsenide. So leakage current in case of gallium arsenide, it is very much less as compared to silicon based diode and germanium based diode. Okay, so in this figure we are seeing that the reverse leakage current I naught, it is 5 picoampere. These are the typical values. 5 picoampere, this is 10 picoampere, and this is in microampere range. This is 1 microampere. These are the typical values of I naught, that is reverse leakage current in case of germanium, silicon, and gallium arsenide based p-n junction diode. And also we are saying that the breakdown voltage, this is the breakdown voltage. The breakdown voltage, that is the reverse breakdown voltage in case of gallium arsenide, it is very much high as compared to silicon and germanium. In this figure we are seeing that the breakdown voltage is minimum for germanium based p-n junction diode, and it is maximum for gallium arsenide based diode. Okay, so this is the VI characteristics of p-n junction diode based on these three semiconductor materials. Temperature dependence, on VI characteristics. So with the increase or decrease in temperature, what will be the effect on VI characteristics of a p-n junction diode? So we will see that. This is forward bias voltage, this is reverse bias voltage, this is forward current, and this is reverse leakage current. Again microampere, this is in milliampere, this is in volt, and this is again in volt. Okay, so we can see that this is the VI characteristics of a p-n junction diode with temperature variation. Here T2 is greater than T0 and T0 is greater than T1. Okay, say this is at 125 degree centigrade, say this is at 75 degree centigrade, and say this is at minus 75 degree centigrade. Okay, so T2 is greater than T0, again T0 is greater than T1. So in this figure VI characteristics, we are seeing that first what is observed, that in forward bias the VI characteristic shifts towards left at a rate of 2.5 millivolt per degree centigrade in temperature. Okay, so we can see that, see this is at 75 degree centigrade. Now if the temperature is increased, then this VI characteristics shifts towards left. shifts towards left at the rate of 2.5 millivolt per degree centigrade. Okay? Now, what happens in reverse bias? In reverse bias, see, with the increase in temperature, in reverse bias, what happens? I naught or IS, which is reverse saturation current, it is doubles with 10 degrees centigrade rise in temperature. You can write it doubles, IS or I naught, it doubles with every 10 degree centigrade rise in temperature. So we can say that, say this is at T naught. Suppose T naught it is at 75 degrees centigrade. It is T2 it is at 125 degrees centigrade, and it is say minus 75 degrees centigrade. Now earlier the graph is like this. With the increasing temperature, this I naught or IS, which is reverse leakage current, it increases. How much? It increases, it doubles with every 10 degrees centigrade rise in temperature. So in this figure also we are seeing that this reverse leakage current, it is in the range of 10 picoampere. Okay. Now with the increase in temperature, now it is in 1 microampere range. Okay. So we can say that I naught it increases with the rise in temperature, and also we are seeing that with the rise in temperature, the breakdown voltage, this is the breakdown voltage, the reverse breakdown voltage, it also increases. So in reverse bias condition, so we can see that in reverse bias, what happens? I naught or IS, it increases with increase in temperature, and this is first. And second, this reverse breakdown voltage, it increases with the increase in temperature. In this figure we are saying that with the increase in temperature, this is at T2, say at 125 degrees centigrade, T naught say it is at 75 degrees centigrade, and T1 it is at say minus 75 degrees centigrade. Okay. So in this figure we are seeing that with the increase in temperature, this reverse breakdown voltage, it increases, and also the reverse leakage current, it also increases. So this is the temperature dependence on VI characteristics of a PN junction diode. Okay. So this graph satisfies this equation. ID it is equal to I naught into e to the power Vd by eta Vt minus 1. In forward bias condition, ID it is approximately equal to I naught into e to the power Vd by eta Vt. This is in forward bias condition. Similarly, ID in reverse bias condition, it is approximately equal to minus I naught. Okay. So the graph VI characteristics is based on this equation. from this diode current equation, we can roughly write ID in forward bias condition and in reverse bias condition. Okay, so this equation satisfies the VI characteristics of a PN junction diode. Okay.